Hello and welcome to Math 135. This is Tracy and we are going to go ahead and do a couple of examples with normal distributions. We are going to use the TI graphing calculator to find probabilities and to find percentiles with our graphing calculators. I encourage you to do this because it is so much easier than using the tables that were created back in the day before we had this kind of technology. All right, let's go ahead and get started. So here's our first example, and this is based on an example from another stats text. I did research this, and this actually happened, and this was the important information. In 2004, a water taxi sank in Baltimore's Inner Harbor, killing 5 and injuring 16. The safe passenger load for the water taxi was 3,500 pounds. At the time, in 2004, it was believed that the mean passenger weight was 140 pounds, based on data from 1960, 44 years before. Based on that 1960 data, the taxi was allowed to carry 25 passengers. In 2004, it was found that the weights of men in the U.S., just men, mind you, this isn't the entire population, but this is important because what if you had a load of all male passengers? So in 2004, it was found that the weights of men in the U.S. were normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. This is much higher than the assumed mean weight of all passengers of 140 pounds. In 2018, just last year, average weight for men was closer to 196 pounds, which is even bigger than the 172 pounds in 2004. And for women in 2018, it was found to be 169 pounds. So if the boat was full and the mean weight of the passengers was 140 pounds, how much weight would the ferry be carrying? So if the boat was full and it had 25 passengers, and the mean weight of the passengers was 140 pounds. Now that means that you could assume every passenger weighed 140 pounds, or you could assume some were heavier and some were lighter, but everybody on average was 140 pounds. So to find the full weight that the ferry would be carrying, you would just take the 25 passengers multiplied by 140 pounds. And when you do that, 25 times 140 is that 3,500 pounds. A full ferry of 25 passengers with a mean passenger weight of 140 pounds would be carrying 3,500 pounds, the safe passenger load. That was considered the maximum safe passenger load. So in 2004, it was found that the weights of men in the U.S. were normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. It is really helpful when dealing with normal distributions to sketch your normal curve, to label the peak with the mean, to go one standard deviation above and below the mean and label those data values on your horizontal axis, to go 2 standard deviations above and below, to label those tick marks, and to go 3 standard deviations above and below and label those tick marks. And that's what we do. Here we have the normal distribution for U.S. men's weight in 2004. The mean was 172 pounds, and there we have the peak weight in pounds for the peak of our normal curve at 172. If we go up 1 standard deviation, 172 plus 29 is that 201 pounds that is labeled right where that curve starts to kind of change. It goes from, it's called an inflection point, but you just kind of see where it's from curved down like an umbrella to kind of start scooping up like a cup. That's 1 standard deviation above and below the mean. And then 2 standard deviations above and below, it starts to flatten out. 3 standard deviations above and below, there's not much left. Those are the tails of your curve. And it's just so much easier to do our problems when we can see this curve in front of us. So, what would be the z-score for a man in the U.S. weighing 140 pounds in 2004? Now remember, a z-score is the number of standard deviations you are away from the mean. A positive z-score means that you are above the mean, and a negative z-score means that you are below the mean. Remember, we have a formula for the z-score. We take the data value and subtract the mean to find out how far our data value is from the mean, and then we divide by a standard deviation to figure out how many standard deviations we are from the mean. So here, we can see from our sketch that 140 pounds is just below one standard deviation below the mean. 143 is one standard deviation below, so 140 is a little bit lower than that, a little bit more than one standard deviation below the mean. So go ahead and do our calculation, data value minus the mean, 140 pounds minus the mean of 172, and that will be a negative number because 140 pounds is below the mean. Divide that by 29, how big a standard deviation is, and we get that our z-score is negative 1.10. So a man weighing 140 pounds is 1.10 standard deviations below the mean weight of 172 pounds. So a 140-pound man, it's not exactly unusual, but it's definitely below the mean. All right, now we want to find the probability that a randomly selected man in the U.S. in 2004 weighed more than 140 pounds. The probability that a randomly selected man weighed more than the assumed average weight for a passenger. And again, this becomes really important when you are loading up a water taxi and you have a group of all men. Again, use your graphing calculator to find this. It is so much easier than using the tables. Here's the sketch that we have. We want the probability that a randomly selected man weighed more than 140 pounds. So we go to that normal distribution that we sketched. We draw a vertical line segment at 140 pounds, and we want the probability a man who was randomly selected weighed more than 140 pounds. So we want to shade in the area under the curve that is above 140 pounds. That shaded area is the probability that a man who is randomly selected will weigh more than 140 pounds. So our notation for that is a capital P, and then in parentheses, x is greater than 140. That's the probability that the value of our random variable is greater than 140, where our mean, mu, is 172 pounds, and our standard deviation, sigma, is 29 pounds. Now that's a lot of area shaded in. That's a good chunk of the area under the curve. So that's going to be pretty high. What does that look like to you? 3/4, 4/5, 9/10, something above 75%, something maybe close to 85 or 90%, 0.85 or 0.9. Alrighty, so we are going to go ahead and use our TI graphing calculator in order to calculate the probability that a randomly selected man in the U.S. in 2004 weighed more than 140 pounds. Now remember that for this problem we have a normal distribution. The weights of men in the U.S. in 2004 was normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Now since we are dealing with a distribution, we are going to go ahead and use our second favorite button on our calculator for this stat class, the distribution button. So second vars will bring up our distributions, and we know we want to use one of the normal distribution functions, but which one? Well, we will always be using number 2 if we are calculating a probability. Never use number 1. In this class, we will never use that number 1 button, so just ignore that. You can either arrow down and hit enter or just type in number 2 to pull up our normal cumulative distribution function. Now we need to fill in the bits and pieces. To do this, it's much easier if you have the sketch of your normal curve with your mean and your standard deviations labeled, and if you've shaded in the area representing the probability we are trying to find. We want the probability that a man weighs more than 140 pounds. So we shaded in all of the area under the curve to the right of more than 140 pounds. So when we fill in these pieces here, what is our lower bound? What is the leftmost edge of the area that we've shaded? Well, that's the 140 pounds. Upper bound. What is the rightmost edge of the area that we've shaded? Well, that area is everything to the right of 140, on and on forever. We're not going to worry about what's the biggest man in the U.S. weigh or any of that business. This is a theoretical curve, and so we are going to assume that it goes to the right forever. We have not said the probability a man weighs between 140 and some upper value. No, it goes on forever. But our calculator does not have a forever. We do not have an infinity button. So we just need to type in a ridiculously huge number. Good simple example, 10 raised to, there's our little caret symbol to tell us we are giving an exponent, to the 99. That's a 1 with 99 zeros after it, which is so outrageously huge that it might as well be infinity. Alrighty, go ahead and enter our mean and the standard deviation. Remember, a mean of 172 pounds and a standard deviation of 29. And paste this onto our main screen. Now, if you have one of those calculators that does not prompt you for all the pieces, then in the notes that you will bring to your exam, make sure you write down normal CDF, open parentheses, lower bound, comma, upper bound, comma, mean, comma, standard deviation, close parentheses. And then maybe remind yourself, if the upper bound is infinity, type in 10 and then that little caret symbol to the 99, just to remind yourself. Now, when you go ahead and hit enter and get that probability, it should match up with the area that you shaded in. Now, if you look at the area we shaded, that's well over half. So when we hit enter, we should get a number that's well over half. In fact, we get 0.865, blah, 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 which is about 87%. Not that far from 90%, a little less than 90%. So yeah, we shaded in most of the area under the curve. Not quite 90% of it. All right, as always, if you have any questions, please let me know. And here we have a screenshot that shows us all of the keystrokes and what your screen will look like when you perform the calculation. And as you can see, yes, the probability that a randomly selected man weighs more than 140 pounds when the mean weight is 172 and the standard deviation is 29 pounds is 0.865, almost 87%. And here is the answer that we said. The probability that a randomly selected man in the U.S. in 2004 weighed more than 140 pounds, which was the assumed mean weight of all people in the U.S. when the safety limits were created, was about 87%. What are the ramifications if you have 25 men wanting to board that ferry with a safe passenger load of 3,500 pounds, assuming that each passenger on average weighs 140 pounds? Just think about that. All right. Now, what is the probability that a randomly selected man in the U.S. in 2004 weighed less than 175 pounds? Again, it is helpful to sketch this normal curve with the area representing the probability we are interested in. The probability that x is less than 175, the probability that the value of our random variable is less than 175, the probability that a randomly selected man weighs less than 175 pounds, shaded in. So again, we draw a vertical line segment at 175 pounds and shade everything less than that, everything to the left. Now that looks like just a little bit more than half of the area is shaded in. Alrighty, let's go ahead and use our TI graphing calculator to find the probability that a randomly selected man in the US in 2004 weighed less than 175 pounds. So just like in the example before, weights are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. We are going to go ahead and find a probability using a normal distribution. So we will use the distribution button here. Second, vars. This is a normal distribution, so we will use the normal cumulative distribution function to find a probability, number 2. And now we need to go ahead and fill in the bits and pieces. So when we look at that area that we shaded in on the previous slide, the lower bound is the leftmost part of the shaded area. Now, if we look at this, we want the probability that the weight is less than 175 pounds, which means we shade from 175 to everything to the left. And that means we don't start somewhere. That leftmost bound goes all the way down to negative infinity. And if you've reset your memory, your calculator will already have its representation for negative infinity plugged in there for you. However, if you've been using your calculator, you might have some other stuff in there, like the 140 from the last problem we did. So you might need to type in the negative infinity yourself. Or, well, we don't have a negative infinity, so the number that might as well be negative infinity because it's so ridiculously small, meaning it is so ridiculously huge in the negative direction. So we are going to use this button here to show that we are getting a negative number. Make sure you are using the correct negative button, or else you're going to get an error. If you use the symbol up here, that means minus. And if you try to stick it in front of a number as if it were a negative symbol, you're either going to get a wrong answer or an error. Okay, so negative, and to show infinity, we are again going to pick a number, 10 raised to the 99. That's a negative 1 followed by 99 zeros, so outrageously huge that it might as well be infinity, but in the negative direction. All right, now look back to that area we shaded in to represent men weighing less than 175 pounds, and we see that the upper bound, the rightmost boundary of the area that we've shaded, is that 175 pounds. Okay, now let's go ahead and enter our mean. It's still 172 pounds. That's what the average man in 2004 weighed. And the standard deviation, same standard deviation we had last time. And go ahead and paste that onto the main screen. Again, if your calculator doesn't prompt you for all the pieces, normal CDF, parentheses, lower bound, upper bound, mean, standard deviation. Don't forget all those commas. And make yourself a note. If my lower bound is negative infinity, use negative, and maybe make a note what that symbol looks like. 10 raised to, remind yourself of that caret symbol, the 99. Now when we go ahead and hit enter, the number we get for the probability should match the area that is shaded under the curve. So when we look at that area shaded under the curve, if we went from negative infinity to our mean of 172, that'd be 50%. That'd be half of the curve shaded in. If we went 172 and above, that'd be half the curve shaded in. But no, we want from negative infinity to a number a little bit above the mean. a little bit more than half of the area under the curve shaded in, a probability of just a little bit over 0.5, 0.54, blah, blah, blah. All right, as always, if you have any questions, please let me know. And here is a screenshot showing you the keystrokes and what you should get on your screen and your answer to this problem. And we can see that yes, indeed, the probability that a man weighed less than 175 pounds when the mean was 172 and the standard deviation of 29 pounds was 0.54, which is about 54%. Very much what we saw in our sketch. So what kind of ramifications does this weight information have on water taxis? In 2004, new safety limits were imposed for the water taxi. Instead of 25 passengers being allowed, only 20 passengers were allowed on that water taxi that could safely hold 3,500 pounds. Do you feel that these new limits were appropriate, and why or why not? Well, here's some helpful information. If we take that safe load of 3,500 pounds and divide it by 20 passengers, well, we're fine as long as the average weight for our passengers is 175 pounds. And that's 3 pounds heavier than the average weight for men in 2004. So I feel a lot better about that, especially if you have a mix of men and women. Although I have to say, I'd really rather make sure that the person who is loading people on the water taxi realizes that that number of 20 passengers comes from assuming an average weight of 175. He might decide that, hey, if a football team is coming on the water taxi, maybe 20 people isn't a safe load. So I like the limits being there as guidelines. Me personally, I'd like to make sure that the person boarding can say something like, no, 20 is the max, but we can go lower if needed. Also nice to know that if we take that 3,500 pounds divided by the average weight of men in 2004, 3,500 divided by 172, we get 20.35 people of average weight. Average male weight that we could load on the taxi. Okay. Do you feel that these passenger limits are still appropriate now in 2019? Do you feel comfortable saying, oh yeah, we can put 20 people, when now in 2018, a year ago, the average male weight in the U.S. was found to be not 172 pounds, but 196? Do you think that we can go with those old limits, or is this something that should be updated on a regular basis? All right, now we are switching gears to a new example with our normal distributions. Suppose men's heights are normally distributed with a mean height of 69.0 inches and a standard deviation of 2.8 inches. How tall should a doorway be if we want it to be tall enough for all but the tallest 5% of men? So now not only are we looking at a different example with a different thing that we're measuring, we're not looking at weights anymore, now we're looking at heights, and we are no longer being asked to find a probability. We want to find a height. How tall should a doorway be? We're not looking for a percentage chance or a probability of selecting somebody of a given height. We want to know how high, what height we should have to contain all but the tallest 5% of men. So it's again a good idea to make ourselves a sketch. Create our normal curve with a mean of, 69 inches, that's what's given. Go a standard deviation above and below, label that on our curve. Go 2 standard deviations above and below, label that on our curve. Go 3 standard deviations above and below and label that on our curve. If we want to know how tall our doorway should be so that it is tall enough for all but the tallest 5% of men, well, let's look. Where are the tallest 5% of men? They're in the right tail of our curve. And yeah, we don't know exactly what 5% is, so we kind of guess. And we draw a vertical line segment there. And we say, we don't care about these men. They can duck. They can stoop. We just want the doorway to be for the rest. So our doorway does not need to be tall enough for those 5% of men. We want the doorway to be tall enough for the rest of the men, the 95% who are below this magic height that we are going to find. We are going to use our calculator to find, because again, tables are a pain and our calculator does it so easily. So, we're trying to find a data value such that 95% of the values lie below it. Does this sound familiar? A value such that 95% of whatever it is we're talking about lies below it? Yeah, that's just the 95th percentile. Now I know I said before our calculators don't do percentiles. Do this in Excel. Well, guess what? If we have a normal distribution, our calculators do find percentiles. They don't for just random stuff. They don't for lists of values. They don't for data of things like counties. They only do for things that are normally distributed, or we'll use another distribution later. So the next slide is a video link on how to use our calculator to do that. Alrighty, let's go ahead and use our TI graphing calculator to find a percentile when we have a normal distribution. Now remember before I told you that to find percentiles you would use Excel because our calculator doesn't find percentiles, and it doesn't for just some random data set. But we can find percentiles when we have a normal distribution. And a percentile is a data value such that whatever percent of the data lies below it. Now remember the problem we're working on. We have men's heights that are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches. How tall should a doorway be if we want it to be tall enough for all but the tallest 5% of men? Now we saw in the last slide that 5%, well, we're not trying to find the 5th percentile because 5% of men are above this magic data value. We want the 95th percentile. We want the height such that 95% of men's heights are below the number that we find. So again, normal distribution, go to our distribution button, second, vars. This time we are not calculating a probability, so we don't want a distribution function. Number 2 is not going to help us. We want the inverse normal function, the INV norm. So right there at number 3. Now here, we want the area below our data value. We want the whatever percentile as a decimal. So 95% of the men are below this height. That's the 95th percentile, which this is the same as 0.95 for the area that we want to have shaded in. For this problem, our mean was 69.0 inches and our standard deviation was 2.8 inches. So now we are going to go ahead and paste this onto our main screen. Again, if your calculator does not prompt you, inverse norm, parentheses, the percentile as a decimal, or the area below the data value we are seeking, the mean, the standard deviation. Go ahead and hit enter. And when we look back at the normal curve that we had sketched and we put in our mean and our standard deviation above and below and said, okay, we want to have only 5% of the area on the top chunk of the curve and 95% below, well, yeah, 73.6 inches sure does look like the height where 95% of men are below 73.6 inches and the tallest 5% of men are above 73.6 inches. All right, again, if you have any questions, please let me know. Calculator. Here is a screenshot of the keystrokes to hit and what your answer will be. So the inverse normal of 0.95, that means the 95th percentile, for a normal distribution with a mean of 69 and a standard deviation of 2.8 is 73.6. Remember, this is not a probability. This is not a percentage. This is a data value. And because we were looking at heights and we wanted to know how tall, and our 69 and 2.8 were inches, this is inches. A doorway should be 73.6 inches tall if we want it to be tall enough for all but the tallest 5% of men. 95% of men are shorter than that. Their heights are lower, so they should be able to fit through the doorway without ducking. All right. Again, as always, if you have questions, please let me know.